Now here we want to prove that cosine theta plus I sin theta to power n is equal to cosine of n theta plus I sin n theta. That is to say that this n will come down and multiply by the angle, and the same thing happens this. We want to show that this is true. Actually, this is from the Moivres postulate in the set of complex numbers. Okay, now we're going to do this using the first principle of mathematical induction. And the first principle states that for each n in the set of natural numbers n, okay, that Pn is a statement and P1 is true. That is to say that the statement given or defined by the first element in the set of natural numbers is true, and also for all k, that is for any arbitrary element in the set of natural numbers, okay, that pk are true for all of them. All right, now thirdly, we consider that the successor of this element is also true, say k plus 1. For example, now we have p of 2, okay, so the successor of 2 is 3, that is just 2 plus 1. The successor of 4 is 5, so the successor of 100 could be 101. So the successor of any element is 1 plus that element, and we also show that this is true. Then if these three things are satisfied, definitely for any n in the set of natural numbers, that this statement is true. Okay, great. Now let's go on to use this first principle of mathematical induction and show that the P statement is true. Okay, first of all, we have to verify this. We have to say for n equal to 1. Okay, so where n is equal to 1, that is P1, that would mean that P1 would be, all right, now I want you to notice that this is just Pn, okay? Take note that this is Pn. Sorry about that, this statement. So for P1, that simply means just put 1 in place of n. Okay, so we're going to have cosine of theta plus I sine of theta raised to power 1. Okay, you know, it's the same thing as not even raising it. All right, and it is equal to, now this cosine of n theta, so that is in place of n, we now put 1, that's just cosine theta, cosine of theta, you know, 1 times theta is just theta, plus I sine theta. So it's the same thing, and it is given that this and this are the same, right? Even from here, so we give that this is true. Okay, so the first has been satisfied, that the left hand side is equal to the right hand side. All right, so for the second statement now, that since this is true, then let's assume that for n equal to k, then pk is true. Pk should be true. That simply means we will have cosine theta plus I sine of theta, all raised to power k. Okay, so this will be given to be equal to, right there, just have cosine of k theta plus I sine of k theta. All right, okay, just like our n functions, let me just put here in red. Actually, it's the same thing. All right, here we have that this will be this. Okay, we assume, remember assumption, and we have that this is true. So if this is true, then how about the third statement for successor of k? So we have p k plus 1. It should also be true. Then p of k plus 1 should also be true, and it is given to be cosine of theta plus I sine of theta to power k plus 1. All right, so we notice this to be equal to what? This right here, you know, in place of n, it just put k plus 1. So we have cosine of k plus 1 theta plus I sine of k plus 1 theta. Okay, all right, now right here, I'm going to expand this. All right, I'll clean this right here, and I'll make use of this to show that this is equal to this. Okay, so this is the proof now. Let me clear this right here. Now for the third condition, we have that P of k plus 1 is true. So we just have this, okay, where we have here to be end. So in place of n, we now put k plus 1. And you know that we're going to solve this to get this. Okay, so a situation whereby we simplify this right here and we get to this, then we know that this statement right here is true. Okay, great. Now let's go ahead and expand this. Now you take note of this power. Okay, the power now becomes k plus 1. So you just notice that this is the same thing as saying k raised to power k times cosine of theta plus I sine of theta. Okay, great. Now you notice that this and this are the same thing as this. So we go ahead and notice that this way here is k, we're going to have cosine of theta. Okay, remember the second statement that this was true. We had here cosine of k theta plus we make this to be black, plus I sine of k theta. Great. Times cosine of theta plus I sine of theta. Now you notice, okay, recall that when we're having k here, we put cosine of k theta plus I sine of k theta, you know, just like this. That's what we said when we're showing for the second statement. The second statement right here. Okay, now we're going to multiply these two brackets. We're going to multiply them and ahead, group them together for what we're going to have. So we have this times this. Okay, you know how you're going to multiply. We have this to multiply with this, and at the same time go ahead multiply with this. And right now we have this to multiply with this. At the same time go ahead and multiply it with that. So we have cosine k theta, cosine k theta times cosine theta times cosine of theta. You go ahead this times that. That is plus I sine theta times cosine of k theta, plus we go ahead this times this. We have I sine of k theta cosine of theta. Now go ahead this times this. You know, I times I is giving us -1 minus now sine k theta and sine theta, sine of k theta. Okay, it's just sine of k theta. Now here we're gonna group the real parts and the imaginary parts. So this and this are the real. So we have cosine of k theta, cosine of k theta, cosine of theta, plus, sorry, it's negative right here. You know, where 1 times 1, I times I is giving us -1. That's just minus sine theta, sine k theta, sine theta times sine of k theta. Okay, plus now we group these imaginary parts together, the part with the I. We take the I out, we have sine of theta cosine of k theta plus sine of k theta cosine of theta. Alright, now I want you to go ahead and see that this could be gotten from the trig identity, where we have cosine of what? You know, theta plus k theta. And the same thing is applicable here. Sorry, not the same thing. Sine of theta plus k theta. Now, if you expand this, you're going to have this. And if you expand this, you're going to have this. So this plus this. Okay, now you go ahead and notice that theta is common here and theta is common here. So we can simply say cosine of theta. I put my bracket and put 1 plus k. Okay, plus I of sine of theta is also common here. So I can put my theta out. And I have here 1 plus k. Okay, great. Now right here, we notice that this is the same thing as this, you know, where addition is commutative in the set of natural numbers. So we have this and this are the same. Therefore, we've proven that this is equal to this, which shows that this is equal to this. for any n belonging to the set of natural numbers. Therefore, this is true. Thanks for watching. Please subscribe to this.